We'll begin by taking up concepts from the first couple of lessons of our text in a single recording. I call these topics together the mathematical tools of the trade, and I assume you've been exposed to them in previous science and math courses. We'll address them quickly in a cursory fashion. Lesson 1 is entitled Units, Scientific Notation, Significant Digits, Estimating with Scientific Notation, and Precision of Calculation. We'll begin with units and scientific notation. In the United States, we make common measurements using English units such as pounds and feet, and other sets of units with relationships based on historically significant but not necessarily simple or uniform equivalencies among each other. For instance, there are 16 ounces in a pound, there are 5,280 feet in a mile. On the other hand, most of the rest of the world deals with kilograms and meters, and the relationships among those units are based on factors of 10. In this course, we'll almost exclusively work in MKS units based on the meter, the kilogram, and the second. These are also called SI units for Système International, and I'll be referring to their prefixes regularly. In lower grades at this particular institution, you may have learned the mnemonic, King Henry died by drinking chocolate milk, the beginning letter of each word indicating the metric multipliers, kilo, hecto, deca, base unit, deci, centi, milli. There's another mnemonic I know that spans a much larger range, and it goes like this. People never understand my cleverness by kicking my grandmother's teeth. The first letter of the words hint at the multipliers for pico, nano, micro, which is symbolized by the lowercase Greek letter mu, which looks like a Roman U with a long line in front of it, milli, centi, base unit, kilo, mega, giga, and tera. You'll see that all these multipliers, except for centi, are separated from the adjacent one by a power of 3. Of course, I assume you know how to handle scientific notation, so if you have questions about that, please review what you know, talk to your colleagues, or come speak with me. Let's talk now for a moment about significant digits or significant figures and the precision with which we make calculations. While we won't emphasize significant figures in this course, we do want to be aware of them. Basically, significant figures are a way of communicating precision of the instruments we make to use measurements. Some people confuse precision with accuracy. Precision has to do with the degree to which our measurements are repeatable and how closely we're able to make a measurement. The finer the scale on our instrument, the more precise our measurement is. On the other hand, accuracy deals with how closely our measurement lies to the true value of the quantity we're measuring. In this figure up here with the 4 targets, we illustrate accuracy and precision using several projectiles that are fired at it. It's possible for measurements to be both precise and accurate, meaning that the measurements are on target and they're all close to each other. But you might have a miscalibrated instrument that makes very reproducible measurements, but those measurements are inaccurate. That's what's shown in this second figure. Alternatively, you might collect a set of accurate but imprecise data, meaning that on average your work is on target, but the results are not really close to each other. That's what's illustrated here in the third diagram. And finally, you could have inaccurate results and imprecise measurements, in which you have a lot of room for improvement in your experiments. That's what's illustrated in the fourth diagram. The last topic in lesson 1 deals with estimating. And the bottom line is this. When we make what I'll call back-of-the-envelope calculations, estimating a value to the nearest order of magnitude is a skill you'll find useful in all areas of science and engineering. There's a famous incident I'd like to share with you which involves Enrico Fermi, the Italian-turned-American scientist who estimated the strength of the first atomic bomb explosion in the New Mexico desert in the White Sands Missile Range. If you've never heard of Enrico Fermi, I encourage you to keep your ears peeled for him. He's an important character. Here are his own words. My observations during the explosion at Trinity on July 16, 1945. On the morning of 16th of July, I was stationed at the base camp at Trinity in a position about 10 miles from the site of the explosion. The explosion took place at about 5:30 a.m. I had my face protected by a large board in which a piece of dark welding glass had been inserted. My first impression of the explosion was the very intense flash of light and a sensation of heat on the parts of my body that were exposed. Although I did not look directly towards the object, I had the impression that suddenly the countryside became brighter than full daylight. I subsequently looked in the direction of the explosion through the dark glass and could see something that looked like a conglomeration of flames that promptly started rising. After a few seconds, the rising flames lost their brightness and appeared as a huge pillar of smoke with an expanded head like a gigantic mushroom that rose rapidly beyond the clouds, probably to a height of 30,000 feet. After reaching its full height, the smoke stayed stationary for a while before the wind started dissipating it. About 40 seconds after the explosion, the air blast reached me. I tried to estimate its strength by dropping from about 6 feet small pieces of paper before, during, and after the passage of the blast wave. Since at the time there was no wind, I could observe very distinctly and actually measure the displacement of the pieces of paper that were in the process of falling while the blast was passing. The shift was about 2.5 meters, which at the time I estimated to correspond to the blast that would be produced by 10,000 tons of TNT. Enrico Fermi had a knack for making roughly accurate estimates with very little data. Therefore, such estimates today are sometimes referred to as Fermi estimates. Why do we bother with Fermi estimates? Because if your estimates are likely to be off by a factor of 2 or even 10, then what's the point? The point is this. Often, getting an estimate within a factor of 10 or 20 is enough to make a decision. And so Fermi estimates can save you a lot of time, especially as you gain more practice at making them. So now let's work a specific estimating example. Here's the problem, example 1.7b. Estimate the answer to the following. And the problem is 9,745 times 5.98 times 10 to the 24 times 0.00293, all divided by 9.22 times 10 to the minus 31. Generally speaking, your strategy should be this. You should round each of the numbers that you're combining to the nearest power of 10 with one significant figure, and write those numbers in scientific notation. Once you've done that, then you want to follow the rules of multiplying and dividing with scientific notation and come up with an answer that's to the nearest one significant figure. So in this example, I'm going to round each of these numbers. 9,745 is nearly 10,000. 5.98 times 10 to the 24 is 6 times 10 to the 24, and 0.00293 is about equal to 0.003. Downstairs, 9.22 is about equal to 9. So I'm going to rewrite the problem. And now that I've done that rounding to one significant figure, I'm going to write each number in scientific notation. And now I'm going to use the regular rules of multiplication and division for numbers in scientific notation to come up with an estimate. So upstairs I have 1 times 6 times 3, that's equal to 18. When I have numbers that have exponents, powers of 10, multiplying by each other, I add the exponents. So upstairs, 4 plus 24 is 28, plus negative 3 is 10 to the 25th. Downstairs I have 9 times 10 to the minus 31. And now what I do is I see 18 divided by 9 is equal to 2. 10 to the 25 divided by 10 to the minus 31 is equal to 10 to the 25 plus 31. So my final answer is 2 times 10 to the 56th power. Let's go back and actually enter the numbers in the original problem in the calculator and see what we come up with. I end up with 1.897 times 10 to the 56th power. Our estimate is very close to that value. So learn to estimate by rounding things to the nearest significant digit and then putting them together. That's the point of these estimates. Now let's move on to the next lesson. Lesson 2 is entitled Trigonometry, Unit Multipliers, and Dimensional Analysis, and the Structure of Matter. Lesson 2 reminds you about basic trigonometry, which is based on right triangles, dimensional analysis, which involves unit conversions, and the concepts of mass, volume, elements, compounds, mixtures, and states of matter. You'll want to remember the mnemonic SOHCAHTOA and its meanings. In a right triangle, you have a 90-degree angle and two other angles. And if you choose one of those other angles, you can label the different parts of the triangle. You have the side that's opposite the right angle, which is known as the hypotenuse. You have the side that's touching the right angle. That's the adjacent side, that's not the hypotenuse. And finally, you have the side which is not touching the angle, that's not the hypotenuse, and that is the opposite side. And this mnemonic, sine, cosine, and tangent, is meant to remind you of the trig ratios. You should know those trig ratios cold when you see them in a right triangle. You also ought to know the Pythagorean Theorem. For the right triangle that's illustrated, h is equal to the square root of a squared plus o squared. And we'll be using that quite a bit. You'll want to remember the quadratic formula. If you have a quadratic equation in the form ax squared plus bx plus c is equal to 0, where a, b, and c are coefficients of the quadratic term, the linear term, and the constant term, then you get two roots that are solutions to this equation. So that x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. You'll also want to know the meanings of these words: mass, volume, element, compound, mixture, and state of matter. Now let's just quickly work through a few examples. Example 2.1a. Find the unknown angle theta and the sides of the triangle shown below. And they give you a diagram. In this triangle, we see it's a right triangle. We're told what the adjacent side of this triangle is. It's 42 centimeters. And we see the opposite side of this triangle is 19 centimeters. And r is the hypotenuse. We want to know what is the measure of r and what is the measure of the angle theta. I can use the Pythagorean theorem to figure out what the hypotenuse is. And now I'll use my calculator to figure out the measure of the hypotenuse. And I get that the hypotenuse is about 46.1 centimeters. Usually we'll find that rounding to 3 significant figures in this course will be good enough for us. Now I want to figure out the measure of the angle theta. I know a number for the opposite side and for the adjacent side, and the trig function that relates those two together is the tangent. So I write the trig function down. And now I use the inverse function or the arc function. I find the arc tangent of the ratio 19 divided by 42. Put the numbers into my calculator, and I find that the measure of the angle theta is just over 24 degrees. Let's take a look at another example. Use unit multipliers to convert 40 miles per hour to meters per second. What I like to do when I have problems that have units, numerator and denominator, is to write one set of units clearly in the numerator and the other in the denominator, and then use equivalencies to figure out what the multiplication should be. That means I need to know what the conversion factors are. So I happen to know that 1 mile is about equal to 1609 meters. I don't necessarily recommend that you memorize a lot of conversion factors in this course, but this one comes up over and over again, and I think it's a really good one to know. This one is a good one. Another good one to know is that 1 inch is equal to 2.54 centimeters. And one more, 1 kilogram is about equal to 2.2 pounds. If you know these three, then that will get you between metric and English units. I also happen to know that 1 hour has 3,600 seconds in it. Or you could say 1 hour has 60 minutes and 1 minute has 60 seconds. So 60 times 60 is 3,600. What I do now is I arrange these things in such a way that I get rid of the units I don't want and end up with the units I do. So I want to put the meter and mile with the meters upstairs and the miles downstairs so that the miles cancel. And then I want to put the hour units upstairs and the second units downstairs so that I get rid of the hours. Now I put these things into my calculator and come up with a number. What this tells me to do is to take 40, multiply it by 1609, multiply it by 1, and write that number upstairs. Take 1 times 3,600, write it downstairs, then take the upstairs divided by the downstairs. Here's what I get. I get that 40 miles an hour is about equal to 17.9 meters per second. One more example. Use unit multipliers to convert 6 square meters into square centimeters. This one's a little more tricky because I have to deal with square units. If you ever handle units that are squared or cubed or raised to some power, I encourage you to actually show the power explicitly with the units, because that will guide you as to what you have to do with the conversion factors. Now, I happen to know, since King Henry died Monday drinking chocolate milk, that 100 centimeters is equal to 1 meter, which means that 100 centimeters squared is equal to 1 square meter. So that means I'm going to have to take and put my centimeters upstairs and my meters downstairs, but I have to square that entire conversion factor. And that squaring, or that raising of your conversion factor to a power, is the thing that makes this problem difficult. Let's put this in our calculator and see what we get. I get 60,000 square centimeters is equal to 6 square meters. So we've covered the first couple of lessons. What we've done is to refresh ourselves on some elementary mathematics, and we're beginning to scrape the rust off of our knowledge from past courses. For now, that's it.